Okay, guys, let's try to keep this short and easy, painless. So what I want to do today is to discuss the homework, and I want you guys to have an advantage. So please ask as many questions as you want. Let's try to make this clear. There is a typo already, so I will fix it. I haven't put it up online. This is what I want you guys to do. So we have 1.5 hours to understand this. This is a Cholesky factorization. I want you guys to implement such a thing in Matlab. What is such a thing? It's a function that takes a matrix A. A is a symmetric positive definite. In case you don't know how to create a symmetric positive definite matrix because you don't remember what I said last week, I wrote it. So in order to create a symmetric positive, wow, fancy. Okay, in order to create such a matrix, super fancy, this is what you can do. So there is no excuse not to create. Okay. Then what do we want to do? We want this function to partition our matrix. A is input, L is what I'm trying to compute, into 4 quadrants, where the top left quadrant is empty, is a 0 by 0. And then we start a loop. So let's see if we can do So let's start with the very first instruction, partition. Our A this is our A, okay? For some reason I am using gamma instead of alpha. And so on. Let's say that we go down to n minus 1, 0, n minus 1, n minus 1. So as I partition A on the top, A top left will be equal to try again. Yes, empty. It's a 0 by 0, so it's empty. Okay. A bottom left. Thank you. Empty as well. This is A top right. And so even though this looks like 1, this is actually 0, okay? It's empty. This is 0, it's empty. So gamma 0, 0, gamma n minus 1, 0. All of that is sitting here into A bottom right. Okay, this is the starting point. Then I have a loop. The loop says keep going until A top left is not as big as A. So let's see if somewhere I have defined the matrix, the function M. I am talking about this object here. Let's see if I have defined it somewhere. It should be. It's not, oops, it's nowhere. So this is something for me to do. I have to clarify what M does. M simply counts the number of rows or columns. If we want, we can replace M with size. So M identifies the dimension of A top left and, well, the dimension of the argument. So, okay, we have to perform a loop. We have to repeat this thing over and over. What? Let's forget about computation. Let's just see what the loop is like. Let's assume that we perform no computation whatsoever. So, what is this repartition thing? The repartition thing is telling me that A top left needs to go to A0, 0. It's A0, A top left, arrow, A0, 0. How do I see that? I'm following the thick lines. You see that the thick lines are actually splitting the matrix in 4 pieces. Those 4 pieces are exactly the same pieces as here. So A top left goes into A0, 0. It's simply a renaming. I'm not doing any operation. I'm simply saying whatever it was A top left, let's call it A0, 0. That's it. No operation. A bottom left. Now this is interesting because what was A bottom left? Now I assign 2 names, A1, 0 and A2, 0. What does it mean? It means that my A bottom left, I want to split it in 2 parts. The top part I call A1, 0. The bottom part I will call A2, 0. And what is the size of this part? So how do I identify this? Well, this thing is identified by the size of A11. So A11 is B by B, so A10 is B. And this object here is everything else. So if we are here, at the very, very first iteration, what is A10? What is A20? At the first iteration, A10 is A10 comes from splitting A bottom left. So A10 at the first iteration is?
What's B?
Sorry?
What's the size of B?
B.
Okay. So it's gamma 1, 0 to gamma B plus 1, 0. And yeah, the same size on the.
Gamma 1, 0?
Oh, bottom left.
But A bottom left is right. It's empty, right?
That's right. We just started. A bottom left is empty.
So A10 is empty as well.
Yes, A bottom 0 is empty. Thank you. What is the size of A bottom A10? Yes. B times 0. As I said, we split A bottom left in 2 pieces. A10 is the size of B, and across is 0. So this is B times 0, and A20, it's n minus B, again, times 0. Okay? The interesting one is what happens to the bottom right quadrant. A bottom right, blah. So now we have to split this object into 4 pieces. A11, A21, A22. There is also A12, but it's symmetric, so I'm skipping that. And the size is determined by A11. It's B by B. So first iteration, what is A11? Let's say that our B, for our purposes, is 2. So A11,
Gamma 0, 0. Gamma 0, 1. Gamma 1, 0. And gamma 1, 1.
thank you.
All the matrix of gamma 0 to gamma b minus 1, b minus 1.
Yes. So we took this part, and this is our A11. Now, whatever is down here will be our A21. Up here is 1, 2, but this is symmetric. And down here is A22. Who is still confused about iteration number 1? Okay, then you see that having A11, A21, A11, A22, we can actually do the math here. Over here we need these guys, and we have assigned the names, so we can do the math. But let's forget about math for now. Let's just see what the program, what this slide wants me to do. Again, let's forget about all of that. In the end, what do they want me to do here? First of all, there is an instruction that tells me that whatever was A00 should be put together with A10, together with A11, and all of that should become A top left. Maybe I should plot this the other way around. No, maybe not. Maybe it's okay like this. So, this is what we want to do. Let me turn off the video. So tell me, after having performed this assignment, what is my A top left? Yeah.
Yeah, gamma 0, 0, gamma 0, 1, gamma 1, 0.
All right, A00 initially was 0, was empty, 0 by 0. A10 was also empty. So this whole thing at the beginning was just A11. When you put together, when you pad a 2 by 2 matrix with empty matrices, it stays 2 by 2. So my A top left at the end of the first iteration has grown, and now it's a 2 by 2. You can imagine, maybe not, I'll tell you. Another of the instructions was that A20, A21 have to be compacted together, and they have to become A bottom left. That's the name. So, long story short, A bottom left will be everything from A to 0 down to A n minus 1, 0, and 2, 1, n minus 1, 1. All right. So A bottom left at the top, we had decided that A bottom left was empty. At the bottom of the first iteration, it has 2 columns. And then A02, A12 will become A top right. Can you tell me what you think is still missing, the last assignment? So I assigned A00, A10, A11. So These three guys have been assigned to A top left. These two guys have been, well, let's put this guy too. These two guys have been assigned to A bottom left. Those two guys have been assigned to A top right. What is missing? Yeah, go ahead.
A to 2 goes to A bottom right.
Thank you. What happens to A to 2 during this loop, during this iteration? Up here, it was n by n, and now the size of this guy here is n minus 2 times n minus 2. So it's shrinking. So we are actually making progress. That's good news for us. Let's move on to iteration number 2. So now we have, oh yeah, that's the bottom right, which is gamma 2, 2, gamma 3, 2. And this is, actually this is two of them. Gamma 0, 2, gamma 1, 2, gamma 0, n minus 1, 1, n minus 1. Okay, iteration number 1 is over. I'm going to delete, to erase. So if you have questions, ask now. Let's start again. Top of the loop, we have these assignments. A top left becomes A0, 0. We have to do absolutely nothing. So A top left, so our A0, 0 is our 2 by 2 guy. It's just a renaming. This object here, A top left, now we call A0, 0. Okay. A bottom left, now I have to split it in two pieces. Well, A bottom left now has some meat, so I can actually split it. A bottom left is this guy here. So what is A10? Thank you. What is the size of A20? And say it again, sorry? Minus 4, yes, by 2, precisely. And we are good, we are done with these first two. Now the interesting part is A bottom right. A bottom right becomes 4 different objects. Let's start from A11. Somebody tell me A11, please. Gamma.
Gamma 3, 2 and gamma 3, 3.
Let's keep in mind that we are not doing any shuffling, anything. So I'm just going through the matrix from top left to bottom right. So if here A10 has these guys, A11 is just adjacent. These blocks are just one next to the other. I am simply assigning a name to these guys so that I can do math easily without having any indexing. A21. Just tell me the size of A21.
Same size as A20.
Precisely. I was tricky with the drawing, but it's exactly the same. It's n minus 4 times 2. So finally, let's cut this short. What is the size of A22? Yes. Very well. So we have cut the matrix in 9 pieces again. Now we want to put these pieces back together with these rules. We want to go back to 4 pieces. All right, A top left, what will it be? A top left has to, oh, here you go. A top left has to absorb A00, A10, A11. So, just tell me the size of A top left. Thank you. A0, gamma 00, gamma 10, 3, 0, gamma 3, 3, 0, 3. Okay. A bottom left, you know, it's going to be n minus 4 times 4. And A22, now we'll start from, this is easy, sorry, not A22. A bottom right, this is easy, it's diagonal with respect to A top left, so I know that we'll start with gamma 4, 4. I see that. I go down the diagonal. The next guy is here. Then we go down here to n minus 1, n minus 1. So this is n minus 4 times n minus 4. Let's do just one more iteration because now things change a little bit and then we're through. Okay. This will be 4 times n minus 4.
So we really have to care about A top right because in the solution it will be zeros anyway.
Say it again, do we really need?
Do we really have to care about A top right and update it all the time because it doesn't matter in the computation?
That's correct. In this particular example, we don't care about it. And many other operations, this framework is very general. So if you add an LU factorization, then you would need it. Next iteration, and then we stop. A top left becomes A00. A00 will be 4 by 4. What A10? What is the size of A10 at this point?
N minus 6, 4.
Say it again.
N minus 6, 4.
I disagree. N minus 5? No? We have 2 by 4. I'm asking A10. A10 comes from A bottom left, and we have to split just this portion here. So we know that it's going to be B, so for sure it's 2. That's for sure. And then how wide is this? Well, A10 is right below A00, so this is now 4. That's correct. How about this one? Yes, now this is correct. N minus 6 times 4, yes, not here. What is the size of A11? Thank you. Can we attempt to put some indices? It is 2 by 2. Let's try to put some indices. Thank you. This is easy because this is 4 by 4, so for sure we are right there. Okay, I think you guys got it. How many columns does this baby have here? It's right columns. Sorry? No. It's right below a 2 by 2 block. So for sure it has 2 columns. So I hope you got this. If you didn't get it, you have not one but 2 videos to watch. So there is another little mistake. What I ask you here is to write a function in Matlab that takes a matrix A, this matrix A, and also takes a value B. And the value B is this B here, is the block size. If B equals 1, I say one more time, these are unblocked algorithms. If B is greater than 1, these are blocked algorithms. I want you to write code both for blocked and unblocked algorithms. Or maybe what I'm asking you is to write code for an arbitrary B, so for any B. What do we have in here? This is a triangular solve. This is a circ, it's matrix multiplication. This is a recursive call. Recursive call, okay. This is again an outer product, it's matrix multiplication. Recursive call, same type of product, triangular solve. Oh, nice. Yet one more typo. You have some work to do tonight. These two guys, these two variants, compute the exact same thing mathematically. Since it's floating point arithmetic, you cannot expect to have the same identical result, but by now you should know how far away these objects should be. And let's see what I ask you to do. Please code this up in Matlab. The objective is elegant code, high-level code. I want you to be able to take any B, and also alg. Alg can be 1 or 2. 1 means left, 2 means right. I will fix this. Style readability, okay. Here it's how to generate a matrix. For the recursive call, call your code for block size 1. And now, if you are, the smart question at this point is, if your block size is 1, what is this? What is a Cholesky of that? And you guys have answered this already, so maybe it would not be a smart question. What is a Cholesky of a 1 by 1 matrix? Thank you, it's a square root. So you know how to terminate the recursion. Now I want you to generate a plot in Matlab. What is the plot like? On the x-axis, you fix the problem size, and on the y-axis, you show accuracy. And I didn't go as far as saying what accuracy is, because I'm sure that by now you know what accuracy is. And over here, I want you to experiment with different block sizes. As I said already last week, B is purely for performance reasons. B equals 1, slow as hell. B equals 2, nothing changes. Large B, this is considerably faster, okay?
One question about accuracy. With this method, does it always produce good conditioned matrices? Because the error depends on the condition of the matrix.
These are the best possible matrices you can generate. Yes. So there is no Hill conditioning. There is nothing like that. Yeah. Okay, guys. This is your chance. Ask questions. If you don't ask a question, I move on to the second part of the assignment.
What built-in Matlab functions are restricted?
No, you can do anything. But as I said, these you cannot use Chol. You have to use your own function call. And anything else, yeah, you're free to use whatever. Six? Oh, 0.6. Generate a plot accuracy. I want you to experiment with your code. I want to create a plot where on the x-axis you try matrices of different size. So you put problem size, matrix of size 100, 500, 1,000, whatever. And on the y-axis you come up with something that convinces me that your code is correct. Or correct, yeah, it's doing the right thing. Yeah.
Can you go slide back? I think it's a stupid question, but I don't get it right now. So at the left side, barrier 1, you have computed L10, and on the right side, you don't have L10.
Yeah.
But you use it?
Yeah. Isn't that beautiful? Okay, maybe your question is how can I use an empty matrix? If it's empty, notice that this is at the very beginning, this is b times 0. So b times 0 times 0, b times 0 times 0 times b, it will be a b by b. So this is actually well defined. It's empty, but it's well defined. Are we brave enough to move on to the second part of the assignment? This is Mathematica. And I put together these notes on Gram-Schmidt orthogonalization. Since I didn't want to scare you guys away, I tried not to talk about inner products and anything too difficult. I think what I will do is, instead of reading this, I just give you a demo in Mathematica. Let's start with two vectors. Well, let's call them two elements. E1, I call it, I don't know, one. Not I call it, I assign it to 1, 2, and E2 equals 2, 3. What I want to do, I want to orthogonalize these elements, these vectors. The assignment is for general elements, so in this particular case I'm showing two vectors, but you can orthogonalize anything as long as it's part of an inner product space. Just don't worry, just follow me. Let's define a function that takes two elements and returns a real number. And we define the function as dot. Dot is the inner product. Okay. And then I tell you, so this is a choice, okay? This is something that oh, wow, sorry. This will be the input for you guys. I will give you a list of elements and I will give you a function. And what I want you to do is to implement everything that I do now. So associated with the in, we can define my norm which is, this is always like this. Okay, so the procedure starts like this. I take the first element and I want to normalize it. Normalize it means I want its size to become 1. What is a size? Size is this thing here. Actually, maybe I could call it size. Okay, it's a norm size. So if you look at this size of E1, right now it's not 1. So it's a square root of 5. Since I want this guy to become of size 1, I don't have anything else to do but simply say E1 equals E1 divided by its size. Okay? And now size of E1 should be 1. So I started with E1 being 1, 2, and now it's 1, 2, but divided by square root of 5. So step 1 of the procedure is complete. I have created a normalized E1. Very good. Now what I want to do, I want to shift, well, adjust E2 so that it is orthogonal to E1. What does orthogonal mean? It means that if I compute in of E2 and E1, the result is 0. Whatever this function is, we don't care, or at least you don't care. I just want to shift this, adjust this E2 so that E2 in E1 becomes 0. And if the function in has some properties, I tell you how to do this. We take E2 and we remove some components, some quantity from it. What is the quantity that we remove? Is the inner product between E2 and E1 times E1. So I am computing this mix factor. I'm basically seeing how E1 and E2 interact with one another. This is the meaning of in. Then I say, okay, this is the amount of E1 that I want to take away from E2. Here you go. I have done that. Second step is that now this is a vector. I want to scale it. I want to make sure, I want to ensure that its length is 1. So size of E2, it's not 1. So now we say E2 equals E2 divided by the size. And now E1 and E2 are an orthogonal basis with respect to the inner product that I have defined. What does it mean? So let's see. Size of E1, it's 1. Good. Size of E2, it's also 1. Okay. In E1, E2, 0. Very nice. E1, E1 is 1. E2, E2 is 1. So, process complete. I started from 2 elements and I arrived to 2 different elements. And now these guys have the property that the inner product across is 0 and the inner product on themselves is 1. This is the Gram-Schmidt process. Questions about this? Yes?
Is it the same as just 2 element vectors, just flipping them and just making one of them negative?
Say it again.
Just flipping them and then making one of them negative.
Oh,
2 dimensions.
no, that's a coincidence. So let's try something else. So now we repeat everything. Okay, find the pattern here. So this is the first vector, this is the second. So it's not like that. And by the way, oh, beautiful. Can you please simplify, please? Okay.
Can you simplify it too?
Simply E2. Yeah, I can simplify E2. Oh, so okay, I see your point.
Yes, just in 2 dimensions. Then you can just orthogonalize.
Wow, that's right. That's true because you do this. So in 2 dimension it actually works like that. Ah. Okay. Okay, we don't need to go to 3, we can just stay to 2.
You have a problem with your in function because it's only on 2 dimensions defined.
No?
Ah, okay, I'm sorry.
2, and now we want E1, E2. This is a monster, but we can simplify. Okay. So that's right. Actually, in 2 dimension, you were perfectly right. Yeah. 3 dimension, no patterns. You can extend this to any dimensionality, of course. Do you guys have questions? Here is the assignment. Here I explained what the procedure looks like when you have more than just 2 elements. So if you have 2 elements, you go through steps 1 and 2 that I showed. If you have 3 elements, you go through step 3 as well. And what do? You subtract from your E3 some components, some quantity from in the direction of E1 and some material components in the direction of E2. So from E3 you subtract whatever you have computed so far. You remove everything from E1, everything from E2. You're left with the material, let's say with the quantity only in E3, then you normalize it and you're good. When you have n objects, you have to subtract the components along each of the previous elements of the basis, and then you normalize, and that's it. In the end, this is always true. It's a matrix. On the diagonal, it's 1 because you're computing the inner product of an entry with itself. And outside of the diagonal, it's 0 because these elements are orthogonal to one another. I want you guys to implement this in Mathematica. Since we work in Mathematica, we can abstract. So what you have to write is a GS function with your name that takes a list of elements and a function. A function is the inner product. It's general. I have not written down the rules, but you can be pretty sure that you cannot use for loops, while loops, and stuff like that. And you can try it with vectors and dot. This is what we just did. But you can try more interesting things. For instance, this object here is a way of creating orthogonal polynomials. These are used everywhere if you do finite element methods, if you do approximations. I mean, orthogonal polynomials are ubiquitous. What is the inner product? Well, it's the product of the 2 functions integrated between a 0 and 1. This is just one particular inner product. We can choose many others. I think there's gonna be 0.45. Okay, there might even be a weight function. Just keep in mind that in this case, these objects here are not symbols, those are functions. So 1 is the identity function, is the constant one. X is, I is not the identity, is the constant one. X is the identity. X square, it's the square function, and so on. So those guys are functions. Over here, we are back to vectors, but the inner product now is the inner product with a B matrix in the middle, and that is a symmetric positive definite. This is also very, very common. In this case, B is any symmetric positive definite matrix. You just define it yourself. So what is your function supposed to do? It takes L, that can be any of these guys. It takes an F, so the function is an input, and returns, let's say, an L prime, which is an orthogonal set of elements. That's that simple. I don't want anything else. Questions? Doubts? Since I am extremely nice, it's yes?
Something like modular, if you want to define helper functions, modular is okay?
Yeah, absolutely, yeah. Those are perfectly fine, sure. Since I'm nice, I decided that it's going to be a team assignment, but please, different teams. I don't want the same people to team up again, okay? And the deadline is on Tuesday, so you have a lot of time. The same day I will assign the homework for C. That's going to be the end of the homeworks. And probably I will also assign the final project one of those days. So I will go back my office and fix some of these. I will add maybe a couple of bullets. I will make sure, I will correct all these little things. So here there should be a B, here should be a 2. I don't remember. Oh, I have to specify what M is. What else? I don't remember. Yeah. So the exams I will be right after the semester ends until some other dates. I will tell you, actually I will specify. Not gonna make the mistake of leaving the end open. I will actually give you a tight range this time around. And the project I will assign probably at the same time as the C or maybe a week later. It's pretty flexible, okay?
What will be the main focus for the Mathematica? Elegance or speed? Or
Neither. It's avoiding the procedural programming, so functional style. Yeah.
It's no challenge, right?
No challenge. No challenge. You got into the mindset. No challenge here. Next one up in C, that's going to be a challenge, yes. Merry Christmas. I'll see you next year.